So what I want to do today is say something brief about why I think Gödel's theorem is so important from a philosophical point of view. And then I'm just going to sum up. So then I'll just say something about like what I think we've learned in the class. But it'll be, as you'll see, less material than most weeks. OK, so Gödel's theorem. So we considered two different forms of the theorem when we talked about it. So the first form of the theorem, we talked about it, was one in which you ask yourself the question, is it possible to program a Turing machine so that it just works forever, printing out mathematical sentences, and it eventually prints out every single mathematical truth, and it never prints out any falsity? So in other words, one can think of the program of such a Turing machine as capturing all there is to be said about arithmetical truth. And what the theorem says and what we proved is that the answer is that there is no such Turing machine. That cannot be done. And therefore that there is a very precise sense in which mathematical truth cannot be captured finitely. So you can't have a finite algorithm that captures everything there is to be captured about arithmetical truth. And then the second form of the theorem that we talked about was to do with axiom systems. So the idea is if you want to start proving stuff in mathematics, you have to start somewhere. So pick some axioms. And because you need to know what your axioms are, make sure that your axioms are such that a Turing machine could recognize what's in your axiom set and what's not. And we showed that an easy consequence of the theorem is that if you have an axiom system for the language of arithmetic that's complete, in other words, if it entails every truth, then it's got to be inconsistent. In other words, it has to entail not just every truth, but also every falsity. So I really just think of those two statements of the theorem as different sides of the same coin. It's just, I think of it as a different way of making the same point. OK, but now I'm going to talk about a corollary of Gödel's theorem. It's not something we're going to prove because the proof is non-trivial and it is excruciatingly laborious. So most textbooks just cite other textbooks about how to do like one crucial detail. Like it's that laborious. It's not, I think, that there's anything conceptual very difficult going on. It's just that like it really is a long and cumbersome procedure. So I'm not going to try to prove it, but I do want to tell you guys about it. Here is a question you might ask yourselves. So suppose that you're playing around with new axiom systems. And the axiom systems are non-trivial. So you know, it's not immediately obvious what follows from the axiom systems, what kinds of worlds you'd be describing. It has happened that people seriously propose axiom systems which turn out to be inconsistent. And of course, it's no fun to work with an inconsistent axiom system. I think that Damien talked about one. So you say, OK, here's my axiom. Whenever you have some things, there's a set of those things. So you know, so what could be more natural than that? You know, if you're going to talk about sets, surely that's your axiom. And turns out that's inconsistent. Well, strictly in the form I gave it, it's inconsistent if the world contains two things or more. But anyway, it's very hard for it to be true. So when you're investigating new axiom systems, there's a real risk that they're going to turn out to be inconsistent. So here's one thing that would be cool. Suppose that you could program a Turing machine so that when you give it an axiom system as an input, it decides the question whether it's consistent or not. Then you can say, OK, well, at least in principle, we could get around the problem because you're experimenting. Once you find something you like, you plug it into your Turing machine, see if it's consistent. If it is, you keep working. Of course, I'm ignoring the fact that if there was such a Turing program, it might be massively inefficient. So maybe the universe would cease to exist before the procedure ends. But you would say, well, at least in principle, you could run it. Now, it turns out that a corollary of Gödel's theorem is that that machine can't exist either. So it's not just that there's no recursive procedure for spitting out all mathematical truths and no falsehoods. There's also no recursive procedure for checking whether an arithmetical theory is consistent. And I think that that has really far-reaching implications. I sort of said something at the beginning of the class, like on the first lecture, but I wanted to come back to that now that we've talked more about Gödel's theorem. So this is what I believed when I grew up. So like when I was in high school, this is what I thought. I thought, there's certain things it's very hard to be sure about. So, it's hard to know what the weather will be like tomorrow, for example. For some areas, we have theories which are reasonably good. So maybe, you can't be certain about the weather tomorrow, but, maybe with some probability, we can make a judgment about, say, whether it's going to rain. And you might think that there's some phenomena where things are even more certain. So, if you have a system that approaches Newtonian conditions, then maybe you can use Newton's laws to make a fairly accurate prediction about what's going to happen. Quantum theories are incredibly reliable, but it's hard to be certain that what they say is true. And one way to see that is that we have been wrong. So it's very hard to imagine a more beautiful theory than Newtonian mechanics. So I like it. It's the most beautiful thing there is. It works extraordinarily well in a large range of phenomena, and yet we know that it's false. And it would be presumptuous to expect that that will never happen again. Especially because although the crown jewels of physics work extraordinarily well in most domains, they're rough at the edges. So, for example, the fact that we don't really have a good way of integrating quantum mechanics with theory of gravitation. That one wonders whether a unified theory is going to involve some revision of the theories we have now. So, physics is pretty good. It could be the best thing that humanity has done ever, like physics, contemporary physics. But we can't be certain that what it says is true. So anyway, what I thought when I was in high school is that the place for certainty was mathematics. So, maybe it wasn't as directly connected to the empirical world as physics, but there at least we had certainty. And I think what this corollary of Gödel's theorem suggests is that that's a mistake. So it is simply not the case that we can have certainty in mathematics. And the problem is that if our theories are inconsistent, then they're pointless. Like, whatever they are, they're certainly not true. So if we're not sure whether they're consistent, we're not sure whether they're true. And if we're not sure whether they're true, then we can't be certain. So, to me, that it just upends the way I think about the world. So now there's the issue of, well, if we don't have certainty, then where do we stand? How does mathematics work? And I think that the horrible truth is that at the end of the day, it's like the rest of our knowledge. Our evidence is indirect. So there is nobody who seriously believes that arithmetic is inconsistent. It's not that anyone has a fully convincing proof of this result. And I'll say a little bit more about that in a bit. It's something else, is that we have worked for so long and so successfully for arithmetic, and so many super smart people have thought about it so hard, that we have a lot of indirect evidence that the theory stands. So you can say, well, look, if there is going to be a contradiction, surely we would have found it by now. I think I know what a model for the theory looks like. So you can draw an omega sequence or the beginnings of an omega sequence of dots on the board and say, well, this would be an interpretation of our theory. And if it has an interpretation, then it's consistent. So you can do things like that. But of course, that's not a proof. That's just pointing out that in light of the situation at hand, it's reasonable to assume that the theory is true. And that's arithmetic. With other theories, it becomes even more contentious. And there are theories like set theory, where what the practice consists in is, so the axioms we have are so seriously incomplete that much of the practice consists in suggesting new axioms, and you want them to be as strong as possible, but not so strong that they're inconsistent. So actually, the whole practice consists in trying to come up with reasons for thinking that the new axioms you propose are consistent. So again, we have no certainty. Okay, so so much for concluding remarks about Gödel's theorem. Does anyone want to ask about that before I just sum up? Yes.
So how would a quantum computer fit into all of this, as it's not in the same class as a Turing machine?
Good. I'm so pleased you asked. I'm so pleased you asked. So, quantum computers are cool because, I mean, for many reasons, but one reason is that they bring increases in efficiency. So, for example, whereas you can't factor numbers into primes in an efficient way using an ordinary computer, you can do so using a quantum computer. In fact, the guy who proved that is now an MIT professor. I think he was at IBM when he proved it. Sure. But one thing that quantum computers do not do is compute functions that can't be computed by an ordinary Turing machine. So you compute the same range of functions. It's just that you can compute some of them more efficiently in a quantum computer. In fact, that is what I was hoping there would be time to talk about when Scott Aronson was here. Yeah, it's a shame. It's not what one was hoping for. So, in other words, having a quantum computer is not like having a halting oracle. So, if you have a halting oracle, so suppose that I don't have a halting oracle, but Rose does, then that means that any function that I'm able to compute, she's able to compute, and more. But if rather than an oracle, Rose just has a quantum computer, then she and I can compute the same functions. It's just that she can compute some much faster. And of course, it may be that in practice, that's the difference between being able to do it and not being able to do it. Because maybe it would take me longer than the universe has to live. But there is still a program that I can use such that if I ran it long enough, it would deliver the results. A nice thing about quantum computers is that scaling is an issue, but they are a reality. So I have a friend who's part of a group at Yale who's working on this, and they have, I forget the number, but they've entangled something like 4 qubits. And I may get the details wrong, but they've done something like factored 15 into 3 and 5. So there's the issue of how far this can go. But quantum computers exist. One thing that Scott was telling me about after he visited the class is we were talking about the incentives that governments might have to develop this technology. And what he pointed out, and it's interesting, is that if, for example, you have a nuclear weapon and nobody else has a nuclear weapon, then you're at an incredible advantage. But with quantum computers, that's not quite right. So if the NSA developed a quantum computer, it would be useless unless nobody knew they had it. Because if it's common knowledge that the NSA has a quantum computer, then everyone can switch encryption algorithms. So I didn't know about this, but he pointed out that algorithms exist which are strong enough not to be crackable in practice by quantum computers. So in order for this to be effective, the NSA would have to have a quantum computer without anybody else knowing that it has a quantum computer big enough to crack other countries' codes. So anyway. Anything else about, Damien.
You went to things on a bit of a downer, and I wanted to offer maybe a more optimistic interpretation of things. I take one of the lessons of Gödel's theorem to be that there's a certain kind of proof that you can't give that arithmetic is consistent, where you write down some sentences and you have some syntactic rules. Now, even if you could give a proof like that, you could only be as confident as you were that you'd remembered to use the rules the right way and you'd written down everything right. So I'm not sure why we should think of that kind of proof as particularly special or particularly important. And maybe the right way to think of the lesson of Gödel's theorem is that there are other things which can make you pretty confident that arithmetic is consistent. I think I am much more confident that arithmetic is consistent because I can sort of envision the model than I would be even if someone showed me a syntactic proof. So this is my attempt at a optimistic reading. It's the lesson is don't get too hung up on that particular idea of proof as the thing which is the gold standard. There's lots of different ways of knowing about stuff.
Yeah, it's true that I end this class in a morose mood, but I think that it's partly because that's the starting point of philosophy, and my summary I hope will bring that out. So when things are working fine, philosophers have nothing to do. Physics is working fine, so philosophers have very little to add. It's well, maybe in some places, but when things start to break down, that you can't just use the standards of the relevant practice to decide how to settle the issues. You need to basically show up and think hard and use common sense, and that's what philosophers do. Okay, so on to a summary of what's been achieved. Okay, so I made a diagram this morning, which I'm going to reproduce on the board. So I think of infinity as the central concept in the class. So of course, sometimes we talked about infinity very explicitly. So we talked about first what the right way to think about infinity is. So it's not obvious what tools to use to theorize about infinity. And one thing I pointed out is that one-to-one correspondence is the right way to do it. And that once you use one-to-one correspondence to compare infinities, you can make real progress. And prove these theorems, which they're mind-boggling. I mean, I've said it many times in this class, but you can prove that some infinities are bigger than others. And that, it's remarkable. Not just that. It's that if you ask, well, okay, so how many infinities are there? The answer is infinitely many. And then you say, well, okay, but how big an infinity? And the answer is, well, bigger than any of the ones we've described in class. Okay, so we talked about the notion of infinity. We saw that there's a tool which we can use to theorize about it, which is this notion of 1-1 correspondence. But it turns out that if you try to push things too far, you quickly get to places where it really is unclear what to say. Okay, and then another thing we talked about is Turing machines and computability. And there are all sorts of connections between computability and infinity. A first connection is that you can think of computability as capturing the notion of finite specifiability. So you can think that the functions that you can program a Turing machine to compute are precisely the functions that can be specified finitely. But we also saw that computability leads to an infinite hierarchy of sorts, because not every function from natural numbers to natural numbers can be computed. For example, the halting function cannot be. But if you're giving an oracle that just gives you answers to those questions, then you can compute more functions. But there's still some functions that you can't compute. For example, the halting function relative to Turing machines with a halting function. But you can be given a super oracle, which settles those questions too. And then you can compute more functions, but again, not all. But you can be given a stronger oracle, and so forth. So you have this infinite hierarchy of bigger and bigger, of more and more powerful oracles. And we notice this very cool connection between these more and more powerful oracles and bigger finite numbers. Because we noticed how if you have more and more powerful oracles, then you can define more and more powerful versions of the busy beaver function, which you can use to specify bigger and bigger finite numbers and win a big number competition. So there's this weird thing where you start ascending in the computability hierarchy with bigger and bigger oracles, and indeed you ascend up to infinite levels, because what we saw is that you need not stop at the kth oracle for k a natural number. You can keep going into the like omega level oracle and omega plus 1th and so forth, like up all of the recursive ordinals. And that allows you to specify bigger and bigger finite numbers. So it turns out that a good method for finding a big finite number is to identify a big infinite number, a big recursive ordinal, use that to specify a big oracle, and use your oracle to specify a big number by way of a big busy beaver function. So like there's this deep connection between finding big infinite numbers and finding big finite numbers. And of course, computability is intimately connected to Gödel's theorem. In fact, as we proved it here, Gödel's theorem just is a theorem in computability. It's the theorem that a certain function is not computable. Okay, and then we had this slightly separate discussion on decision theory. So it's the issue of if you have different choices, what ought you to do? The crucial kind of case that we discussed to get clear about these issues was time travel. And the reason time travel was important was that it allowed us to separate two issues that seem closely related, but in fact are different, and it's important to keep separate. So remember, there's Bruno going back in time and thinking about killing his grandfather, and there's the issue of what he will do on the one hand, but also the issue of what he would do if he made a different decision. And keeping those things apart allowed us to make good decisions about what decision theory to adopt, and also to say something about what free will is all about. I mean, to echo Damien's earlier point, there too I ended on a pessimistic note. So what I suggested, and I reiterate that this is controversial amongst philosophers, is that once you start thinking about free will seriously, and in particular, once you start thinking of it in the context of our discussion, including free will, for example, then it's easy to end up with the conclusion that there's less to free will than one might have thought. Because it's very tempting to think that free will is somehow incompatible with determinism. So the idea is that if you live in a world where knowledge of the laws and initial conditions is enough to deliver knowledge of everything that's going to happen in the future, there could be no free will in that world. But the very distinction between what will happen, say, given the actual evolution of the universe, and what would happen under certain counterfactual assumptions, say, my deciding to do something different. That distinction suggests that maybe free will is not incompatible with determinism after all. So then free will is just a different kind of beast than one thought it was. So a suggestion that I put on the table is that it's enough for someone to be free, that there be a possibility in which they make a different decision and act otherwise. So it's in a way disappointing because the world seems like a less magical place. But sometimes the price of clarity is disappointment. And when we talked about decision theory, we eventually faced the boogeyman of decision theory, which is to do with non-measurable sets. So cases like the hat problem, in which we use the axiom of choice to produce this weird construction, and ended up with a result that probabilities are not well defined. And that's connected to decision theory because in a case where probabilities are not well defined, the issue of what ought you to do can go ill-defined too, because often the issue of what you ought to do is taken to be connected to how likely it is that if you do it, that will happen, how likely is it that if you do it, that will happen, and so forth. And then you average up, and that gives you the expected utility for your action, and you use that to make up your mind. But if it turns out that probabilities are not well defined, then it could be that what you ought to do is not well defined. And of course, non-measurable sets are creatures of infinity. So none of those problems emerge when you focus on finite sets of possibilities. So I think that this is another example of a case in which our standard theoretical tools, things like probability theory and decision theory, work very well under normal conditions. But when put under stress, and in particular under the stress of infinity, they stop working well. And then it's like totally unclear how to proceed. And philosophers take over. So I think the, if you needed to put the lesson of the class very briefly, what you could say is that there is a wild and wonderful world out there, including infinity. And it can be tamed to some extent. So there are lots of cool things that can be proved about it. But it's also pretty wild in the sense that once you allow yourself to think about infinity, then you enter terrain where some of the theoretical tools just don't work that well. And it becomes less clear what to say. And I think if I had to pick one thing that I wanted you guys to leave this class with, it's modesty about what our theoretical tools can do. So I think that science is so successful that it's easy to assume that it knows no bounds, that it's all powerful. And I think at MIT it's especially easy to leave with that feeling of optimism. And I think part of what we've seen is that that's true in practice in many realms. But actually, like, the edges of our knowledge are pretty messy. And that means that there is a lot of foundational work to be done. So that's it. Unless if people have questions, I can answer questions. Otherwise, we can stop. Yes.
I know that it's a long answer, but when you are talking about Gödel's theorem, we might say that there is something wrong with our definition of truth or our definition of proof. And then you can establish all these different relations with all these other topics. So I'd like to hear from you, what do you think? Where is the problem? The truth or the proof?
Ah, yes, you're thinking like a philosopher. So what Saul has done is leave no assumption unquestioned. We're running into difficulties, and he says, well, why not just revise the way we think about truth, or revise the way we think about proof? I think that these are all real options. So one person who has pursued them seriously is the guy I mentioned earlier, and who I interviewed and added the interview to the lecture notes. So his name is Graham Priest, and he's basically an intellectual radical. So what he thinks is that modifying very basic theoretical tools like our logic holds the answer to some of these issues. And the things he modifies are so fundamental that he ends up modifying things like what we mean by truth, or, depending on how you do it, what we mean by proof. I myself am not convinced, not because I think that the proposal can't work in principle. I think in principle it could work. It's just that I've so far been disappointed with the results. So, you can't just revise your logic and leave it at that. If you revise your logic, you have to show how, like, you can still, do science, so that you can, somehow live a rich theoretical life within the new system. And I just think that people who suggest these very radical revisions to our way of thinking haven't succeeded in doing that. But I think the problems are hard enough that that may ultimately be the way forward. We're going to have to wait and see.